Hey everyone, it's Suraj, and today we're going to be walking through discussion 6 for the spring 2019 iteration of Data 100. Okay, so this discussion, it assumes that you already know the basics of random variables, expectation, and variance. So if you don't already know that, I'd highly recommend, looking at the lecture slides, or I have the slides that I used in discussion when I taught this discussion in person, linked below. But on Piazza, there are also slides from other TAs. So make sure you look at one of those resources before watching this video if you're unsure on expectation and variance and that sort of stuff. But okay, let's dive into it. So question 1, suppose John visits your store to buy some items. He buys toothpaste for $2 with probability 0.5, and he buys a toothbrush for $1 with probability 0.1. Find the expectation of the amount he spends. Okay, so X is the total amount he spends. Okay, and what I'll say is that the total amount he spends is equal to, why don't we say P plus B, right? Where P is the amount he spends on toothpaste, okay, and B is the amount he spends on a toothbrush. Okay, and what I can do is take the expectation of both sides here and say that the expectation of X is just the expectation of P plus B. But then I can use the linearity of expectation to separate the expectation of a sum into a sum of expectations. So the expectation of the total amount he spends is the expectation of how much he spends on the toothpaste plus the expectation of how much he spends on the toothbrush. So now all we need to do is find these quantities individually. Okay, so the expectation for how much he spends on the toothpaste. Remember, this is just a weighted average of outcome times probability of that outcome. Okay, so he buys toothpaste for $2 with probability 0.5. So we have outcome, which is $2 times probability. And here we're sort of implicitly told that with the remaining probability, he just doesn't buy the toothpaste. Okay, so either he buys it for $2 with probability 0.5, or he just doesn't buy it. So that's 0 times 0.5. That doesn't really change the sum, right? Which gives us 1, because 2 times a half is 1. Okay, similarly, the expectation of how much he spends on the toothbrush, well, that's $1 with probability 0.1. And then with the remaining probability, he just doesn't buy it, so we're left with 0.1. Okay, and so now I can say this is 1 plus 0.1, which is 1.1. So the expectation of X, where X is the total amount he spends, is 1.1. Okay, pretty straightforward. Now question 2 is significantly more involved. Okay, suppose we have a coin that lands heads 80% of the time. So what I'm going to do, just to simplify our notation a little, is say P is 0.8, and let the random variable Y be the proportion of times that the coin lands heads out of 100 flips. Okay, so not the number of times, but the proportion, okay? So for example, if the coin landed heads 23 times, the proportion would be 0.23. Okay, what's the variance of Y? Okay, so first what I want to do is define these indicator random variables, which are really just Bernoulli random variables, xi. Okay, and they'll have the Bernoulli distribution with parameter p. And so what this means is xi will be 1 with probability p and 0 with probability 1 minus p. Okay, and so if xi is equal to 1, it just means flip I was a head. And if xi is equal to 0, it means flip I was a tail. Okay, in this case, I could really replace this with 0.8 and 0.2. Okay, so I'm modeling each individual flip with this random variable xi that takes on the value 1 with probability 0.8 and 0 with the probability 0.2. And so if I were to sum x1 plus x2 all the way through x100, because I'm looking at 100 flips, that would tell me the total number of heads, right? Oops. Total number of heads. But since we want the proportion, I should take that sum and divide it by 100. Okay, so y is 1 over 100 times the sum of x1 through x100. And why are we looking at the sum? Well, it's because each individual one, right, x1, x2, so on and so forth, through x100, is either equal to 1 or 0, right? It's each flip is a head or a tail. So if we sum these ones and zeros, it'll tell us the total number of heads, right? Because if, like, for example, 72 of them had the value 1, it would tell us that we had 72 heads, right? Because the zeros don't contribute to our sum. And so we sum them, that'll tell us the total number of heads, divide by 100, it will tell us the proportion of heads. Okay, and now all we want is the variance of y. Okay, before we get into calculating the variance of y, just a couple of facts about the Bernoulli distribution, right? The expectation and the variance. Okay, also sometimes students ask this, is there a difference between using square brackets and your regular parentheses for expectation and variance? No, there isn't. Okay, the expectation of a Bernoulli random variable with parameter p is just p, and the variance is p times 1 minus p. Okay, and again, if that idea sort of seems foreign, I recommend you look at the slides linked below or the lecture slides or one of the other resources on Piazza. Okay, but we'll need that in our solution. So now what we want is just the variance of y. Okay, so what I can do is just take the variance of both sides and say this is the variance of 1 over 100 times the sum of I going from 1 to 100 of xi. Okay, now the first rule we're going to use is this, the fact that the variance of a times x is a squared times the variance of x. Okay, and that's sort of a property that you can use, you can derive on your own, but when you have a constant times that random variable, when you take the variance of it, you have to square the constant when you pull it up. Okay, and how does that, why is that relevant here? Well, it's because we can write 1 over 100 squared times the variance of this sum. Okay, now the next rule we'll have to use is the fact that if x and y are independent, then the variance of their sum is a sum of their variances. Okay, this is not an if and only if. For it to be an if and only if, we would have to say uncorrelated instead of independent, but we won't really get into that now. All we really need to know now is that if two random variables are independent, variance of the sum is the sum of variances. And well, why do we need that here? Well, it's because each coin flip is independent, right? Whatever happens on flip 73 doesn't really impact whatever happens in flip 74, for example, right? Each coin flip is independent of one another. And so what that allows me to do is rewrite the variance of a sum as a sum of variances, okay? And again, variance is not linear, right? Because when I pull out the constant, I have to square it. So this property is not called the linearity of variance, okay? Because it's not linear. You could call it the separability of variance or something like that, but we won't really worry too much about the semantics. And so I can write this as the sum of the variances of xi. And now, to proceed, we notice that each xi has the exact same distribution, right? They all have the same Bernoulli distribution with parameter p, and that means all of these variances are the exact same. They all have the variance p times 1 minus p. Okay, and there's 100 of them, so I can say this is 100 times p times 1 minus p. Okay, you notice the 100 on the numerator and denominator cancel out. Before we had a 100 squared, so now it's just 1 over 100. So we have p times 1 minus p over 100. But remember, p was just 0.8. So this is really 0.8 times 0.2 over 100, which is 0.16 over 100. which is 0.0016. So that's the variance of y, where y is the proportion of flips that were heads. Okay, so this solution uses a rather elementary approach, and it doesn't really assume that we know what a binomial distribution is. If you know what the binomial distribution is, this problem is made a lot simpler. Okay, and just as a quick walkthrough, we won't be as detailed. Okay, so using the same definition of these Bernoulli random variables up here, binomial random variables are just sums of individual independent Bernoullis. So if I said x was the sum x1 plus x2 plus x100, x actually has the binomial distribution with parameters 100 and 0.8. Okay, so n is 100, p is 0.8. And the variance of a binomial distribution is just np 1 minus p. Right, in this case being 100 times 0.8 times 0.2. Well, sure, that's good. We have the variance of x, but our question really deals with y, right? But x and y are related due to the fact that y is just 1 over 100 times this sum, which is just 1 over 100 times x. So the variance of y is the variance of 1 over 100 times x, which by the fact that we have to square the constant when you pull it out of the variance, gives us 1 over 100 squared. So is the variance of x, which is 100 times 0.8 times 0.2 over 100 squared, which is the exact same thing as we had before, just without these added steps. Okay, so either way, you'll arrive at the same result for the variance of y, but it turns out you can do it without assuming any knowledge of the binomial distribution. You can do it just from using the Bernoulli distribution, which is interesting. Okay, so that's problem 2. Okay, cool. Now let's move on to number 3. So we're told that x is some random variable with expectation equal to mu. Using the definition of variance as being the expectation of the squared distance of x from its mean, show that for any constant c that this equality holds. Okay, so what we could do is start with the left-hand side and manipulate it and show that it's equal to the right-hand side, or start with the right and show that it's equal to the left, or just work on both and arrive at some middle ground. But what I'll do is start with the left-hand side and show that it's equal to the right-hand side. Okay, and this proof will revolve around the fact that we can write x minus c as x minus mu plus mu minus c. Okay, why is that valid? Well, I just added mu and subtracted it, so it's equal, but you can sort of already see why this might be necessary. So let's dive into it, okay? So you have the expectation of x minus c, quantity squared, which I can say is the expectation of x minus mu plus mu minus c squared, and since it's addition, I can sort of add these parentheses wherever I want. And now you can think of x minus mu as being a and mu minus c as being b. So inside the parentheses, we have a plus b quantity squared, which we know expands to a squared plus 2ab plus b squared. And so we can make that simplification. And now we have x minus mu squared plus 2 x minus mu minus c plus mu minus c quantity squared. Okay, now we have an expectation of a sum of 3 terms, and by linearity of expectation, I can separate this into a sum of 3 individual expectations. So I can call this the expectation of x minus mu quantity squared plus I can say expectation of 2x minus mu minus c, but 2 and mu minus c are just constants, right? And we know for expectation, the expectation of a constant times x is just the constant times the expectation, because expectation is linear. So what I can do to make things even simpler is, say, this is 2 times mu minus c times the expectation of x minus mu. Okay, and then plus, now mu minus c is just some constant, right? Because mu is some fixed value, and c is also some fixed value, so mu minus c squared is just some constant, and the expectation of a constant is just the same constant. So I can drop the expectation for the last term, and I have mu minus c quantity squared. Okay, now matching this up with what our goal is, we notice we already have the first term, mu minus c quantity squared, and we already have the second term, expectation of x minus mu quantity squared, right? Because we know that that's just the variance of x. By definition. Okay, so now all we really need to do is show that this middle term equals 0. Okay, and how we can go about doing this is looking at this last term, the expectation of x minus mu. Okay, by linearity of expectation, we can separate that apart to be the expectation of x minus mu, right? Because mu is just some constant. But then we see the expectation of x is the same thing as mu, and mu minus mu is equal to 0. And so we're left with just what we're looking to find, mu minus c quantity squared plus the variance of x. And we're done. Cool. Now let's move on to number 4, which revolves around the result we have in question 3. Why don't I just copy, I can write it out. We'll need this. So the expectation of x minus c quantity squared is mu minus c quantity squared plus the variance of x. Okay, and I'll separate this question into part A and part B, okay? So in part A, we want to show that the variance is the minimum value of this quantity for any c. So what this is saying is that give me any real number c, the variance will always be the smallest possible value. In other words, if c is equal to the expectation, it will take on the smallest possible value. Okay, and there are two ways we can do this. One is using this equality that we found in the last part, and there's another way we can do it using calculus. Okay, and we'll do both ways now. Okay, so one, using expression. Okay, and so why don't we start with this again? Expectation of x minus c squared is mu minus c quantity squared plus the variance of x. And we know mu minus c is just some constant again, and it's squared, meaning it's non-negative. It's greater than or equal to 0. Okay, which means we can write that this is greater than or equal to whatever we would have if we got rid of the mu minus c quantity squared, because this thing right here is non-negative. Okay, and I can just ignore the non-negative part and say that this line is greater than or equal to this line. Okay, and that's really a proof of this equality, or inequality rather, right? And we've shown exactly what we needed to show. Okay, and again, we can also do this another way using calculus. Okay, and what we really want to show, again, is that the variance is the minimum value of this function, right? And this is just an abstract drawing. I'm not saying that this function actually is a parabola, but what we're essentially saying is that suppose we have some axis, we're saying the minimum value of this function occurs at y is equal to the variance of x. Okay, and we're saying this is true for any c. So really, we're saying that this occurs when c is equal to the expectation, right? Because if in this expression c is equal to the expectation, the inequality becomes a strict equality, right? The equality holds when c is equal to expectation, right? And so what we can do is say that this is some function of c, and when we take the derivative of this with respect to c and set it equal to 0 and solve for the optimal value of c, we'll find that it's actually expectation of x, okay? Showing that expectation of x is the minimum, is the optimal value for c. Okay, so let's do that. So we can take the derivative with respect to c. So f prime of c is equal to, well, actually before that, let's simplify things a little. Okay, so we have the expectation of something minus something else squared. I can expand this out to x squared minus 2cx plus c squared. And remember, c is just some real number scalar constant. Now, using linearity of expectation, I can say this is the expectation of the square of x minus 2c, the expectation of x, plus c squared. Because remember, c squared is just a constant, and the expectation of a constant is just itself. Okay, and now remember, we take the derivative and set it equal to 0 with respect to whatever variable we're trying to optimize. And this will be a common theme when we look at optimizing loss functions in future discussions. Anyways, I take the derivative with respect to c. What's the derivative of this guy with respect to c? Well, it's 0 because it's independent of c. And what's the derivative of negative 2c expectation of x with respect to c? It's just 2 expectation of x. And what's the derivative of c squared with respect to c? Well, it's plus 2c. And we're setting this equal to 0, and we want to solve for the optimal value of c. Okay, we can, add 2 times the expectation of both sides and divide by 2, and it gives us that this optimal value of c hat, which is the optimal, is equal to the expectation of x. Great. And so that tells us that this is one of the critical values of this function. But we don't really know if it's a maximum or a minimum, right? If this value maximizes the function or if it minimizes the function, okay? And so to be rigorous, we really need to look at the second derivative, okay? And what we want is that the second derivative should be positive, which tells us that the function is opening up, concave opening up, which tells us that if a function looks like this, the optimal value that we've approached is actually a minimal because the function is opening up, okay? And so the second derivative is just, if this is the derivative, it's this first term is a constant, and we're left with 2, which is indeed greater than 0. So therefore, the critical point is a minimum. Okay, so what this tells us is that c hat being equal to the expectation minimizes expectation of x minus c quantity squared. And so what that tells us is when we plug in expectation of x here, and really expectation of x is just mu, this quantity, which is just the variance, is the minimum of the aforementioned function. Okay, and just to recap what we did with this calculus approach, we had some function, took the derivative of it with respect to c, set it equal to 0, and found the optimal value of c, and showed that when c takes on this value, it minimizes the function. Okay, and when c takes on this value of the expectation, this function really just becomes the variance, right? Because when c is equal to the expectation here, this thing is the variance. Okay, so both of these are just ways to show that when c is equal to the expectation in this expression over here, it minimizes the expression. Great. And now part B is a little more straightforward. We want to show that the variance can be determined computationally using the formula the expectation of the square of x minus the square of the expectation of x. Okay, well, how do we arrive at that? Well, again, there are many ways we can do that, but what we want to do in this question is sort of start with the inequality we're given, or not the inequality, the equality, and set c equal to 0. Okay, what happens if you set c equal to 0? On the left-hand side, you just have the expectation of the square of x. Here you have mu squared plus variance of x, and you can just rearrange to get variance of x is the expectation of the square of x minus mu squared, which is the same as the other form, right? Because mu and expectation of x are the same thing. Okay, and so that's part B of the question, and that's question 4. Great, now we're on question 5. we're told that we roll a die 9 times and write down the values on slips of paper and then place all of these slips of paper in a box. And we're given some statistics of the numbers, the sum of squares, mean, and median. And for each of these quantities, we want to try and determine them. Okay, so the first one is we want to find the expected value of a single draw from the box. And what that really means is what's the average of all the numbers in the box. Okay, so the expectation of a single draw, and well, we're told the mean, and it's 3. And so that's really it. Okay, another way you could calculate that is take the sum, which is 27, and divide it by the number of slips, which is 9. Okay, but either way, the expectation of a single draw is just the mean of the numbers, it's 3. Okay. B, we're asked for the expected value of the average of 9 draws from this box. Okay, what I'll do is define this random variable xi. It's not an indicator random variable as we had in question 2, right? Because indicator random variables either take on the value 1 or 0. This one will just take on the value of draw I. Okay, so what this means is the first time I pick one of these slips of paper, I get a 4. That means x1 is equal to 4, so on and so forth. Okay, and really, xi has the expectation of 3, right? Because every time you draw it, since we're doing this with replacement, they're independent of one another, and it's just the same as the expectation of a single draw, which is 3. So every time you draw from this box, the average value you'd expect to see is 3. Okay, and now the quantity we want is the expected value of the average of 9 draws. And so what we're going to do is take draws x1 through x9, and we want to find the average of them. How do we do that? Well, we sum them and divide by the number, which is 9. So we want the expectation of x1 plus x2 plus ... plus x9 over 9. Okay, and what we can do is take out the constant 1 over 9, put it out front. So now we have the expectation of the sum going from I is equal 1 to 9 of xi. And we know by the linearity of expectation, we could rewrite an expectation of a sum as a sum of expectations. So I can say this is 1/9 of the sum of the expectations of xi. And since each draw has the same expectation of 3, each of these 9 values, right, the expectation of x1, expectation of x2, so on and so forth, all the way until the expectation of x9, they all have the same value of 3. So you can say this is 1/9 times 9 times the expectation of any arbitrary one, since they all have the same expectation. Usually by convention we say expectation of x1, which is just 3. So not only is the average of a single draw, or the expectation of a single draw 3, the expected value of the average of 9 draws, so you draw from the box 9 times, and keep doing that over and over, so you draw 9 times, find the average, draw 9 times, find the average, draw 9 times, find the average. The average of those averages is also 3. Okay, so something you might think about is how this relates to things you might have seen in Data 8, like sample means versus population means, but you don't have to worry too much about that. That's just a parallel that you might see. Okay, in part C, we want to find the exact variance of the tickets in the box. Okay, so how we can go about doing that is by using the computational variance formula that we established in an early part of this discussion. And we know that the variance is the expectation of the square of x minus the mean squared. Okay, what's the mean? Well, we know that that's 3, and so 3 squared is 9. So all we need to do is find the expectation of x squared. And as an aside, one fact of expectations is that the expectation of x is of course the sum of all possible values of x times the probability that the random variable takes on that value. But the expectation of a function of x is a similar sum, but instead it's the function times the probability. Okay, so the expectation of x squared is a sum over all possible values of x squared times the probability of assuming the value little x. Okay, and what can we use in terms of what's given? Well, we have what the sum of the square is. It's 93. And each of the 9 slips is equally likely because we're told, or we sort of assume that they're all equally likely to be selected from this box. Okay, and so what this equates to is a sum over all the values of x squared times 1 over 9. Maybe I'll write this in red because it's specific to our question. Sum over all values of x squared times 1 over 9, because there's 9 of them, they're all equally likely. And take the 1 over 9 out in front, and I have the sum of x squared, and I'm told that that is 93. Okay, so that means the expectation of the square of x is 93 over 9. Okay, so I have the variance of x is 93 over 9 minus 3 squared. Oops, just to make it a little neater, minus 3 squared. And that should be 93 minus 81 over 9, 12 over 9, which is 4/3. Okay, so the variance of the tickets in the box, okay, is 4/3. Okay, and now in part D, we want to find the variance of the average of 9 draws of the box. Okay, so we can do this in a similar way as we did part B, right? All we really need to do is replace this expectation with the variance, okay? So we can go ahead and do that. Let me clear up some, we can actually do it over here, okay? So what we want is the variance of the sum, well, the variance of 1 over 9 times the sum of xi, with I going from 1 to 9. Okay? And we know that if you want to pull a constant out of a variance, we have to square it. So we have 1 over 9 squared times the variance of this sum. And now since each draw is independent of one another, I can replace the variance of a sum with a sum of variances, as we did in question 2. And now again, since each draw has the same distribution, they all have the same variance, which we determined to be 4/3 in the previous part. So I can say this is 1 over 9 squared times 9 times 4/3. Again, we're doing the times 9 because there's 9 of the same thing. And now, with a little arithmetic, I figure out that the 9's cancel, so I'm left with 1 over 9 times 4/3, which gives me 4 over 27. Okay, so the variance of the average is 4 over 27, whereas the variance of a single individual draw is 4/3. Okay, and again, this brings up the comparison of sample standard deviation versus population standard deviation, and sample variance versus population variance. Okay, there's a lot of parallels between them. Okay, and so that wraps up question 5. And lastly, we can look at question 6. We wish to model exam grades for Data 100 students. We have several pieces of information about them, and what we call these are features. Okay, these are different features that we can use. How many hours they studied. So I can say x1 is hours studied. How many hours they slept before the exam. So I can say x2 is number of hours slept. And x3 could be how many lectures they attended, okay? So number of lectures attended. We want to propose a model to predict exam grades, okay? And we want a loss function to measure the performance of our model, okay? So this is a pretty standard setup. We have a set of features and we want to come up with a model. Okay, and so what we're really saying is we want some function that takes in x1, x2, and x3 and spits out a predicted exam grade. Okay, and really this could be anything we want it to be, right? We could say our prediction is x1 to the exponent x2 minus the sine cubed of x3 times alpha squared, where alpha is some constant, Sure, that is a possible model, but we like to use linear models in this class, and just in general, linear models are favorable. Okay, and by linear we mean linear in terms of the parameters themselves, not in terms of these features. Okay, and that's a distinction you'll become a lot more familiar with in future discussions. But for now, let's think of the most simple model we can, and that's just a linear combination of x1, x2, and x3. It's something times the number of hours they studied, plus something times the number of hours they slept, plus something times the number of lectures they attended. Okay, and so the most basic model we can come up with is just x1 plus x2 plus x3. Okay, number of hours they slept plus the number of hours they studied plus the number of lectures they attended. Okay, but just to add a little bit more flexibility to our model, what we could instead replace this with is constants multiplied by each of them. So we can say theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3, and yeah, we can have that. We can also add a bias term or an intercept term, theta naught. Okay, so this term is often referred to as the bias or the intercept. Okay, it's the b and y is equal to mx plus b. So it's a linear combination of our three features plus some constant. Okay, and that's a totally fine model that we could use. Okay, and now in terms of a loss function, we'll learn about various types of loss functions like L1 loss, L2 loss, the Huber loss, and all of them are equally fine. And what we could suggest is, for example, the L2 loss. You could take the true exam grades, so y actual, minus the predicted ones. Okay, squared. Okay, so for each individual student, we'll have all of this information and we'll have their actual exam grade, right? And the loss is the difference between their actual grade and predicted grade squared. Okay, one little nuance. Oftentimes, we will think of everything in terms of a vector. Okay, so we'll say x will be our feature vector, and it might look something like 1, x1, x2, and x3. And theta will be also a vector that will look like theta naught, theta 1, theta 2, and theta 3. And so our function will really look like f of x is equal to theta transpose x, or equivalently x transpose theta. Okay, and that will give you the same expression as we have here, but usually it won't be written in terms of multiple variables x. We'll just have y minus f of x. Okay, because here x would be a vector. Okay, so that's a potential model that we could use, and this is a loss function that we could use to find the optimal model, right? So find the optimal values of theta. Okay, and lastly, question 7. Suppose we collected even more information about the students, such as their eye color, height, and favorite food. Do you think adding these variables as features would improve our model? Okay, and the answer is most likely no. Okay, and it's because just knowing how exam grades work, students' eye colors, heights, and favorite food probably have no impact on those things. Okay, and that doesn't mean we can't use them as features in our model, right? We could very well just make our model, theta naught plus theta 1 x1, and this is what we had before, right? Up until x3, there's nothing stopping us from adding theta 4 x4 plus theta 5 x5 plus theta 6 x6. Well, this is their eye color. If we somehow made that numeric or used one high encoding or something like that, x5 could be their height. Somehow this could be their food, right? There's nothing stopping us from making that model, and it might lower what we call the training accuracy, right? Lower training accuracy, which means, on the data set that we use to create the model, it will appear to have lesser error, right? But it won't generalize as well, right? Because we know that these features aren't really meaningful, okay? So it won't generalize well. Okay, and the whole point of this question was just to get you thinking about the idea of selecting different features and feature engineering, and this whole idea of training accuracy versus test accuracy and bias variance. Okay, but we will expand upon these ideas much more significantly in future discussions and future lectures. Okay, the whole point of this question is just to get you thinking about that. Okay, but in terms of a concrete answer, do you think adding these features, these variables as features would improve our model? Probably not. Okay, and I think that wraps up the discussion. Don't forget to like and subscribe, and we will see you in the next discussion video.